In this video, we're going to complete the solution using the analytic method. We'll start by reviewing what we've done so far, and then we'll note that the polynomial actually behaves very badly, and we have to deal with it. We'll then figure out how to avoid infinities and how that leads to quantization. And finally, we'll generate the Hermite polynomials, which is this final solution for the analytic method. So the analytic solution that we did last video, starts by changing to reduced position xc, and we're going to get a new Schrödinger equation, which was simplified here to d squared psi dxc squared is equal to xc squared minus k psi. This is a separable solution, which is separable in a product of an asymptotic solution for xc goes to infinity and a polynomial solution which is valid for xc going to 0. And this is the solution that we postulated. Psi is equal to h of xc times e to the minus c squared over 2. And we know this is going to be roughly correct because our solution for the algebraic method gave us things that look like Gaussians, which is very similar to this. So ultimately, we got a defining equation for the polynomial part of the solution, which was a differential equation, and we solved it using a polynomial solution. And that led to a recursion relation of aj plus 2 in terms of a sub j. And the recursion relation looked like this. A sub j plus 2 is equal to 2j plus 1 over k minus k divided by j plus 1 times j plus 2 times a sub j. So if we start with a1 and a0, we get the odd and even terms. And to make up the full solution, even and odd polynomial series will add up to give you the full thing. But there's a problem here. So this is the way our solution looks, and we can generate the coefficients with our recursion relation. The problem is that these solutions are unbounded for large values of xc. And since xc is proportional to x, it's the same thing. At large values, these solutions go to infinity, and that's really bad. And let me show you how that happens. So let's imagine that that j goes to infinity, right? We have an infinite number of terms in this solution. Well, then the recursion relation simplifies. For j going large, this becomes 2j on the top. These are irrelevant. On the bottom, you get j squared. And so you get a sub j plus 2 is approximately equal to 2 over j times a sub j at very large values. Well, if I rewrite this and change the indices, so I'm going to go from j to j minus 2, so this becomes a sub j on this side, and this guy becomes h of j minus 2, and I'll just bring this down in the denominator as j over 2. So what this says is that the jth term, the jth coefficient, which j is very large, is related to the one below in this way when j is very large, right? So it's a sub j is a sub j minus 2 over j over 2. Well, that means that this one now is related to a sub j minus 4 in the same way. So instead of a sub j, instead of j over 2, I get j over 2 times j minus 2 over 2. Similarly, with I can relate this guy to the j minus 6 polynomial, and so coefficient, and I go, it's divided by j over 2 times j over 2 minus 1, which is this, times j over 2 minus 2. And it keeps going like this all the way until you get to either the 0th or the j equals 1 or j equals 0, because you have to add those up. And so that tells me that if I go all the way down to the original start of the sequence, a sub j is going to be approximately equal to some constant, which is whatever that first coefficient is, divided by j over 2 factorial. So this is going all the way down till j goes to 0. It's approximately equal to that. Now, if I take this as the value of a sub j, I can now look at the full solution for large c. So remember, both j goes to infinity and c goes to infinity. Well, h of c for large c is then the sum from j equals 0 to infinity of some constant times 1 over j over 2 factorial c to the jth power. That's just this form here. I just replaced a sub j with this term here. Now, if I now recast this in terms of a different variable called m, where m is equal to j over 2, then I get the sum of m equals 0 to infinity, 1 over m factorial times c to the 2m. This is a geometric series which can be solved, and that geometric series gives me approximately c times e to the c squared. So that's how this goes. When large values of c and j goes to infinity, I get something that looks like c, some constant, times e to the c squared. But this is unbounded as c goes to infinity, right? So the fact is that this goes faster than the exponential decrease, because this is the exponential squared, and before the other part of the solution is e to the minus c squared. So clearly this doesn't go to 0. So how do we avoid that? Well, if we look again at our polynomial sequence, and then we also look at the recursion relation, we see that what we have to avoid is j going to infinity. So we have to stop j somewhere. We have to have a point at which this power series terminates. Right? So we can only solve this problem with c going to infinity by terminating the power series at a highest value j equals n. So that a sub n plus 2 is equal to 0. Fortunately, we can do that because we have a minus sign here. So if we make it such that k is equal to 2n plus 1, then the j plus 2 coefficient will vanish. And once that vanishes, they all vanish. And by terminating that power series, we avoid the infinity that we get at large values of c, because we never go to large values of j. So the condition for termination of the power series is that k is equal to 2n plus 1, where now j has a highest value n, j max. What this does is it results in a quantization of the energy. Because if you remember, k was equal to the energy. K is equal to 2 times E, and now it's E sub n because we have an n, over h bar omega. If I now solve for the energy, I get something that should be familiar. E sub n is equal to n plus a half h bar omega, where n is equal to 0, 1, 2, and so on. So these are exactly the same energies we got from the algebraic solution. And now you can see the quantization has come in from the fact that we've got to avoid infinities and we've got to terminate the power series. Now, unfortunately, this only forces one of the two series, either the even or the odd series, to terminate. And that's easy to see why, because if this condition is met for one value of n is either odd or even, and it can't be the other. So what that means is that the other series has to vanish from the beginning. So a0 must be equal to 0, or a1 must be equal to 0, and the other one can be something that's non-zero. So that means the solutions either have odd or even symmetry. That is, they're either symmetric about the origin or anti-symmetric about the origin, and we can't have a mixture of both. That's not surprising. That's how these functions usually behave. Now, the functions are very sensitive to having the energy quantized. If the energy is taken just to be a little bit different than half an integer multiple of h bar omega, we've got problems. Let me show this to you graphically. If I use 16 coefficients in the sum for the ground state, and then I take delta E is equal to plus or minus 0.001 times h bar omega, if E is equal to 1/2 h bar omega, then this is a very nice solution. If I take E is 0.049 times 0.49 times h bar omega, you see it goes to infinity at large C. If I make it 0.51 h bar omega, then it goes to negative infinity immediately. And no matter how small I make this, if it's anything that's not 0.5, you will find an infinity. So only for this, the ground state, only for 1/2 h bar omega is the solution well behaved at C equals plus or minus infinity. So now we can use this to generate the polynomials given a specific value of n that terminates the series. So let's start with realizing that k is equal to 2n plus 1. We now have a coefficient recursion relation that becomes a sub j plus 2 is 2j plus 1 minus 2n minus 1 over j plus 1 times j plus 2 times a sub j. Or minus 2 times n minus j over j plus 1 plus times j plus 2 times a sub j. So you can see that when j is equal to n, then j plus 2 is the coefficient, j plus 2 is 0. We can now generate the polynomial solutions in wave functions. So for n equals 0, we just have a sub 0, right? Because when n equals 0, then, and j equals 0, then a sub 2 is 0. And of course, a sub 1 must be 0 because that can't be possible. We can only have even or odd solutions. And h0 of c is just the coefficient a0. What about n equals 1? For n equals 1, we have a1, right? And a0 has to be 0 because otherwise you get an infinite series which would blow up. So a sub 0 is 0 for this. A sub 1 is 0 over here. A sub 0 is 0 over here. And so for a sub n equals 1, now you start with 1 here. N equals 1 minus 1 for j gives me 0 for a sub 3. And you just get this coefficient, the 1 term. And then h1 is just a1 times c. For n equals 2, you have a sub j, so you have a sub 2, you start with a sub 0, you get 2 minus 2 is 4 over 1 times 2, so that gives me minus 2 times a0. That's what I have here. I then take, and that makes two coefficients that I have, a sub 0 and a sub 2, and so h2 is equal to a sub 0 times 1 minus 2c squared. For n equals 3, and I'll show you how this works then. For n equals 3, we start with a sub 1, and n equals 3, I get 3 minus j, which is 2, times minus 2, over 2 times 3, which is 6, so I get 2/3, minus 2/3 a sub 1. And if I try to go to a sub 5, then n, which is equal to 3, and j is equal to 3, sends it to 0. And so h sub 3, c, is equal to a sub 1, c minus 2/3 c cubed, and so on. We can go n equals 4, we get a sub 2 equals minus 4a0, and a sub 4 equals minus 1/3 a2. And that gives me a third order, three-term polynomial. H4 is a sub 0, 1 minus 4c squared plus 4/3 c to the fourth. For n equals 5, I have a sub 3 equals minus 4/3 a sub 1, and a sub 5 is equal to minus 1/5 a sub 3. And so I get, when I multiply this all out, h sub 5 of c is a1 times c minus 4/3 c cubed plus 4/15 c to the fifth. Now notice that depending on the value of n, the coefficients of these power laws are different. For example, here at h2, you have minus 2c squared. When you have h equals 4, you have minus 4c squared. Similarly, here you have minus 2/3 c to the third power. Here you have minus 4/3 c to the third power. And so each of these polynomials is going to be a little bit different. It's not that you add another coefficient, you generate all the coefficients starting fresh. These are the so-called Hermite polynomials. And in physics, it's conventional to normalize the Hermite polynomials so that the highest order term in C is positive and with a coefficient of 2 to the nth power. If you look at Wikipedia, this calls this the physicist's Hermite polynomials instead of the mathematician's Hermite polynomials, or the real Hermite polynomials. And so for the physicist, you call them h sub 0 and h sub n. So h sub 0 is 1, h sub 1 is 2c, h sub 2 is 4c squared minus 2, and so on. You see it goes 4, 8, 16, 32, 64, 128, 256, and 512. And you'll notice that this is all odd exponents. This is all even exponents, odd, even, odd, even, odd, even, odd, and so on. And these coefficients get very large, which is why I can see that it's okay for physicists, and mathematicians don't particularly care for these large numbers. They like the smaller numbers and keep them normalized differently. So the complete solutions for the harmonic oscillator then are rewritten in terms of the Hermite polynomials as follows. Psi sub n of c is equal to minus m omega over pi h bar to the 1/4 power times 1 over 2 to the nth n factorial times the Hermite polynomial h sub n of c e to the minus c squared over 2. Now, what do these wave functions look like? I plotted the first 6 states, and you can see how they look. Clearly, it starts even, odd, even, odd, even, odd around the origin. And so this is the ground state. It's just basically a Gaussian. This is the Gaussian times x. And here we have the second order Gaussian, third order, and so on. If we take the square of this, the probability densities, show higher probability density around the classical turning points. And if I go to the biggest value for n equals 60, you see how this really looks like the classical turning point has the highest probability density, which means the oscillator spends more time at the edges, which is what you normally see in a harmonic oscillator.